Sung-Soo from Seoul, and yeah, he's gonna talk about non-Hermitian generalizations of Marchenko-Pastur law. He's gonna go from the circular law from the multi-criticality. So please, Sung-Soo.
Okay, thanks a lot, and also I'd like to appreciate you, Matteo, again for suggesting me to give a talk in this nice seminar. And today I'm gonna talk about global and local statistics of certain Gaussian two-matrix models, which is based on joint work with Gernot Ackman from Bielefeld, and also Namgyu Kang from Korea Institute for Advanced Theory. And okay, so this is the outline of my talk today. And in the first part, I will first introduce the models we are working on, the so-called Ginibre ensembles, and also non-Hermitian Richard matrix model. And actually, in the first part, I will focus on the global statistics, and I will present the limiting spectral distribution of the models. And in particular, I will explain that in the Dirac picture, there exists certain phase transition of the support of the spectrum. And in the second part, I will focus on the local statistics, and in particular, I will present the local statistics of the models when this phase transition appears. And let's move on to the first part. And let me first introduce the model we are working on. And this model is so-called the Ginibre ensembles. And for us, from the mathematical point of view, the motivation of studying this type of model is quite simple. So we would like to discover certain smooth interpolations between very classical results in random matrix theory, namely the circular law in the complex plane, and also the Marchenko-Pastur law in the real line, when we consider the Hermitian matrices. And the precise model we are working on is given as follows. So first, we consider one parameter tau, which is called non-Hermiticity parameter. So this is a parameter which measures the hermiticity of the models. And we consider P and Q matrices, which is n times n plus nu rectangular matrices with IID-centered complex Gaussian entries. So basically, these matrices P and Q are rectangular Ginibre matrices. And here in the talk, we use the conventions that the variance of the Gaussian entries is given by 1/4n. And using these P and Q and the parameter tau, we build two matrices x1 and x2, given by this weighted linear combination of this P and Q indexed by tau. So basically, you can think of these x1 and x2 are sort of Gaussian matrices, rectangular matrices, which are correlated each other. And the Ginibre ensembles we consider is given like this. So in the diagonal term, we have 0 matrices, and in the these Gaussian matrices is on the off diagonal terms. So you can think of what is this is the definition of the Ginibre ensembles, and some remarks is when tau is equal to 1, then you can observe that because there is no term here, so x1 and these two matrices are perfectly correlated in a sense that these are actually same. And so in this case, these correspond to the standard Hermitian Gaussian unitary ensembles. So if you don't know what is this, the model, the Gaussian unitary ensemble, just consider this is the definition of these models. And actually, this model was first studied in the physics community, and actually these Ginibre ensembles usually appears in the context of the QCD, the quantum dynamics, and with chemical potentials. and when they consider the Dirac-Operator spectrums. And some basic properties of this matrix model is as follows. And actually, by linear algebra, so we can see that. So first, we have these are 2n plus mu times 2n plus mu matrix models, and actually, the spectrum always consists of deterministic eigenvalue 0 with multiplicity nu, and the other 2n eigenvalues are of course random. And actually, we can see that these complex eigenvalues always comes in pair. And so this is the basic property. And actually, in the physics literature, there are several studies about these models, but there are actually very few results with mathematical rigor. And so in this sense, our goal is, I think, clear. So we would like to derive what is the explicit formula for the global statistics of these models. And also we would like to say something about the local statistics at certain criticality. So this is the model we are working on. And before stating one of our main results, I will show you the picture of the spectrum. And actually, something different happens depending on the order of the parameter nu. And here, just for the record, nu is the parameter here to define the size of the rectangular matrices. And the first case, when nu is over the small on, then, and also if the parameter tau, this is the non-Hermiticity parameter, and if this parameter tau is equal to 0, then we have the classical circular law. So in other words, as n tends to infinity, then the eigenvalues tends to be uniformly distributed on the unit disk. And for general values of tau in this regime, actually this was known in the physics literature that in this case, for general values of tau, again, the eigenvalues tends to be uniform, but in this case, they are tends to be uniformly distributed on certain ellipse, as you can see in this picture. And of course, if tau is close to 1, then you can see that the matrix model is Hermitian. So in terms of the eigenvalues tends to be close to the real axis. And if tau is equal to 1, then we can see that all the eigenvalues are real. And actually, this follows the Wigner semicircle law. And actually, if you are familiar to the chiral picture, then you can think of this as a Marchenko-Pastur with scared variables. And some more interesting things happens when nu is over the n. And first, when tau is equal to 0, then again, we can see that the eigenvalues are radially symmetric. So the eigenvalues tends to occupy certain disk, as you can see. But in this case, the radius is no more given by 1. But the point here is, in this case, when nu is comparable to n, then the density is no more flat, because you can see that you can actually see from this picture that there are less eigenvalues near the origin compared to the boundary. And also for general values of tau, the shape of the support of the spectrum, which we call the drumlet, is no more given by an ellipse. And more important part here is at certain critical point, so this support of the spectrum reveals this kind of topological phase transition, which I mean at certain critical value tau, in this case 1/2, the drumlet splits into two blocks. So after this critical regime, we have the drumlet consists of these two connected components. And again, if tau is equal to 1, then all the eigenvalues are real, and we have this kind of scaling version of the Marchenko-Pastur distributions. Okay, and our first main result deals with the rigorous derivation of all the stuff in this slide, and we obtain the following theorem.
Sorry,
okay.
Just to clarify, so when nu grows, would you define this this kind of density where the eigenvalues are very rare, around 0? So these are called forbidden regions sometimes in literature, or this is not?
Yeah, okay. So you mean so for instance in this picture?
Yes.
Okay, actually, okay, I will explain this in the next slide. But actually, so you can see there are very less eigenvalues near the origin. But actually, because the density is 0 at the origin, but there is no forbidden region. So actually, so as n really increases, then it anyway occupy all this set. Okay, is it clear?
Yes, thank you.
And so our result gives the following. So basically, we describe what is these limiting spectral distributions, and to describe this, we use one parameter alpha, which describes the ratio of nu and n here, and then we can we prove that the empirical measure of this Dirac matrix, actually the random eigenvalues of the Dirac matrix weakly converges to certain probability measure mu, which is absolutely continuous with respect to the Lebesgue measure, and having these kind of radially symmetric density. And actually, more important part here is we show that we found the explicit formulas for the support of the spectrum, and then we actually show that this support can be described by this polynomial equation of degree 4. So basically, you can think of these kind of curves here can be described in terms of these quadratic equations. And some remarks about this result. First remark is when alpha is equal to 0, then you can think of this is the case that nu is relatively small, so nu is over the small on, and then you can see that there is no term here. Then so we have the flat density, and also if alpha is equal to 0, then actually it is sort of straightforward to check that if for alpha 0, then this quadratic equation actually reduced to the quadratic equations which exactly correspond to the elliptic law as is predicted in the physics literature. Okay, and the second remark is for the positive value of alpha. Then we already saw in the previous slide that there exists certain transitions of the drumlet, and thanks to this explicit formula, we actually discovered that this phase transition appears when the parameter tau, the non-Hermiticity parameter tau, is given by this critical value. So the critical value is given by 1/square root of 1 plus alpha. So again, for instance, in this picture, so this is the case that alpha is equal to 1. So we discovered that this kind of critical regime appears when tau is given by 1/square root 1 plus alpha, in this case 1/square root 2. Okay. And these are some pictures of the one-point functions. So the pictures of the global densities when n is given by 100. And you can see from this picture that actually the density part here is given by, depends only on the distance to the origin. And you can also see that in this pre-critical regime, the support is given by a connective domain. And at this critical regime, we have this kind of lemniscate type domain. And after this critical regime, we have these two distinct components.
So you say it depends. It depends only from the distance on the origin, provided that you are inside of this sort of quartic curve.
Right. So so this is the formula of the density.
Mm-hmm.
So you even though of course the shape of the support is of course not radial symmetric. So this is radial symmetric only when tau is equal to 0.
Mm-hmm.
But somehow the density is given by radial symmetric function. Okay, is it clear?
Yeah. So this dA is just what's it? What is the definition of dA? The measure dA.
So once again, what is dA?
In the main formula, so you have dA of zeta.
Okay, sorry. You mean this one? So this is just the Lebesgue measure.
Okay.
Lebesgue measure divided by pi. So basically the area measure. Sorry. Okay. And is there any other question about the result? Okay, then let me explain another equivalent models we are working on, which is called actually called the non-Hermitian research matrix models. And just for the recall, let me remind that this parameter tau is the non-Hermiticity parameter, and we consider these two rectangular Ginibre matrices to build these two correlated matrices. And in the definition of the Dirac matrix, these two matrices are in the off-diagonal terms. And what we call non-Hermitian research matrices is just given by the product of these two matrices. Okay. And you can see that if tau is equal to 1, then of course this matrix model correspond to the very classical research ensembles. And actually, for general values of tau, this sort of non-Hermitian research matrices was proposed by Ginibre and Singh. So actually, they proposed this model as for the analysis of time series. For instance, when building covariance matrices for time-lagged correlation matrices. But anyway, the point here is there are several motivations in physics to consider this kind of models. And actually, the reason why we call these models and the Dirac matrix, the Cairo-Ginibre ensembles are equivalent is because of the following relations. And actually, this also follows from the linear algebra. And when we consider the non-zero random eigenvalues of the Dirac matrix, which always comes in pair, as I already mentioned before, then the square of these the eigenvalues of the Dirac matrix correspond to the distribution, the eigenvalues statistics of these non-Hermitian matrices. So basically, if we understand one of these two pictures, then we can also understand the other one. And so this is the reason. So the counterpart of the theorem for the non-Hermitian research matrices is given like this. So again, we show. So this is actually the exactly the equivalent formulations. And in this case, the limiting spectral distribution is given by has the density of this form. So there are so you can see that if this point is close to the origin, there are more eigenvalues. And actually, the support of the spectrum is much more simple in this picture because we can see that in this case, actually the spectrum is given by shifted ellipse. So basically ellipse with a shift given by these terms. And again, some remarks about this picture. And actually, for some special cases, this theorem reduced to the well-known densities. For instance, so so basically, the result non-Hermitian result matrix is an example of the product matrices. And if tau and mu is equal to 0, so just again for the record, tau is the non-Hermiticity parameter. So if tau is equal to 0, then we have the radial symmetric. And if this nu is the parameter appearing in the rectangular matrices. So the meaning with 0 is we only consider the square matrices. And in this case of the square matrices, okay, for instance, in this special case, this appears this density correspond to the product of two Ginibre matrices, which was studied by several authors. And also for the radial symmetric case with general values of alpha, this density was obtained by Kanziker and Singh. And you can see that if tau is equal to 0, then this actually corresponds to the certain disk. And of course, this is sort of by definition, if tau is equal to 1, then the model corresponds to the classical result. And actually, we can see that if tau is close to 1, then the height of this ellipse is getting smaller. And actually, this corresponds to the Marchenko-Pastur distribution on the real line. And one small remark is the drumlet is given by an ellipse, and actually we can see that the foci of the ellipse is given by tau, the non-Hermiticity parameter tau, times the left and right endpoint of the Marchenko-Pastur support. So this is sort of the geometry meaning of this non-Hermitian generalization of the Marchenko-Pastur. And again, let me show you some pictures of the spectrum of these result matrices. Again, we think these two distinct regimes. And first, when there is small, then we can see that there, and also if tau is equal to 0, we can see that the eigenvalues have this occupy a certain disk. And actually, you can see here that there are a bunch of eigenvalues near the origin, because if we can see this density. So if alpha is equal to 0, then the density blows up near the origin. So this corresponds to the fact that in this picture, there are a bunch of eigenvalues near the origin. And for general values of tau, when tau increases, then we can see that the eigenvalues tends to occupy this kind of ellipse. And of course, if tau is equal to 1, then all the eigenvalues are real. And we have this classical Marchenko-Pastur distribution with hard edge at the origin, having a local Bessel law. And in this case, in the second case, so let me explain what is the meaning of the critical value in this picture. And you can see that if tau is equal to 0, then we have this the drumlet is again given by a disk. And then before the critical value, then the origin is always contained inside the drumlet. And the meaning of the critical value in this picture is at this critical value, the origin is exactly on the boundary of the support. So in this case, at this critical value, the origin is on the edge of the spectrum. And after, in the post-critical regime, the drumlet is basically on the right-hand plane. And if tau is equal to 1, then we have the Marchenko-Pastur having soft edge at both left and right edge points. And so is there any questions so far about this result?
So I have a question. Basically, it seems to me that you say that all of these results they follow basically by this equivalence in distribution between
right.
that if you take the model that you introduced before and you square the eigenvalues there, then you obtain the eigenvalues of this model that you're explaining now.
Right.
Okay, so also the density, the limiting density mu is also obtained squaring and everything.
Right. So okay, let me give some more explanation. So when we consider the Dirac picture, so if this kind of phase transition appears, so this is basically the relation between these two drumlets correspond to when we scaling. Sorry. When we consider the square root of this drumlet, then basically we have this lemniscate type picture I showed before. And also in this way, when we consider the density by scaling and also consider also the Jacobian, then we have this equivalence between these two pictures. Okay.
Okay. Now it was not clear to me why squaring why squaring the eigenvalues transforms this lemniscate that you drew before in this ellipse, but maybe it's something trivial.
Oh, okay. It's really trivial because so actually, but it's also a great point because I explained here that at this critical value, the origin is exactly on the edge of the spectrum, and if we want the drumlet for the previous picture, so we should consider the square root of this guy.
Okay, so you obtain two pictures.
Right.
Okay.
But in this case, the square root, even though we consider the square root, then it is connected domain.
Okay.
In this case, we have these two distinct connective components. So this is the picture you can imagine.
Okay.
Okay, then let me explain so how we can prove this kind of result. And actually, the most fundamental observation is the Coulomb-Gas interpretation of the models. So I guess many of you are familiar to the two-dimensional Coulomb-Gas, but let me remind what it is. And actually, as in many random matrix models, especially for the Gaussian matrix models, we have when we consider the eigenvalues of the in this case the non-Hermitian VCR matrices, then it follows this sort of Boltzmann-Gibbs law. So this is exactly correspond to the 2D Coulomb-Gas with specific inverse temperature beta equal to 2, and so we have this logarithmic interaction among the particles, and also there exists certain external potential terms here, which is given by these special functions. So okay, here this k nu is the modified Bessel functions of the second kind, and these parameters a and b are related to the non-Hermiticity parameter tau in this way. Okay, so but actually this precise formula for the potential is not that important in at least in this first part. And so when we consider this kind of Coulomb-Gas models, and in particular, if we want to describe the global statistics, we only cares about the asymptotic behavior of the potentials. In other words, we only cares about the dominant term of these potentials. So And actually, in this case, if you are familiar to the Bessel functions, you may also know these kind of asymmetric behaviors when these parameters tends to infinity. And actually, using these kind of well-known asymmetric behaviors, we can see that the dominant part of the potential is given by these asymptotic potentials, which I denote by Q alpha tilde, which is given by somewhat simpler formula. So basically squares and the combination of the squares and the logarithms. And so when we have these kind of 2D Coulomb gas interpretations, and then we can use one of the fundamental results in this business, which is Johansen's marginal measure theorem. And this theorem states that when we consider the empirical measure of the Coulomb gas, then this weakly converges to the equilibrium measure, and this converges to certain probability measure, which is the equilibrium measure of the weighted energy. So, so let me explain what it is. So for given probability measure having complex support, then let's consider this kind of weighted energy functional. So we have these logarithmic terms and also the potential terms here. And actually, you can see that this is exactly, so when you consider again the Gibbs measure here, then you can see that when you consider the logarithm here, then you can see that this weighted logarithmic energy is exactly the continuum version of the Hamiltonian. So, so Johansen's marginal measure theorem states that more precisely, Johansen proved this kind of statement for the Hermitian matrices, so two-dimensional Coulomb gas on the real line, and this two-dimensional statement was obtained by Hedelman and Makarov. So this theorem states that this equilibrium, the empirical measure tends to be the minimizer of this weighted energy functional. So actually, from the physical point of view, this is sort of trivial because the particles tends to minimize the total Hamiltonian. But anyway, this is a well-known theorem. And also, so this is the reason we can convert this kind of so we can convert the problem to find the limiting spectral distribution to purely potential theoretic problems. And actually, so this is exactly the problem, the inverse problem in the potential theory. So we already know the empirical measure converges to this kind of equilibrium measure. So what we have to do is to solve so-called 2D equilibrium measure problem. So in other words, we have to find what is the minimizer of this energy among all the compactly supported probable measures. And so, of course, our claim for the theorem, to obtain the theorem, our claim is as follows. So we actually show that the solution of this equilibrium measure problem is given by this one. So this is exactly the density I showed you before. And the support is given by the shifted ellipse. And also, okay, here I would like to also mention another quite recent papers by Juan, Carrier-Delay, and Arnold Quillers. And actually, in this work, they also consider some other equilibrium problems induced from the sphere. Okay. In other words, they consider exactly this kind of 2D equilibrium problems, but with different types of the potentials. And somehow surprisingly, so this comes from a totally different context, but they also found that the solution of the equilibrium problems is given by certain ellipse. And okay, so now let me explain how we can solve this kind of inverse problem. And to do this, for
Let me,
okay.
sorry, let me ask one question. So, in this, of course, the Johansson's theorem holds for the real case. So you're saying that basically it was proven by, so there were some names you mentioned before. It was proven that this non-Hermitian Marchenko-Pastur distribution that you're considering. So the empirical measure converges to this mu hat, which mu hat is the minimizer of this energy. So this is a theorem.
No, okay, right. So let me explain a bit more precisely. So in both Johansson's case and also Hederman and Markov's theorem in the 2D case, they consider Coulomb gas with general potential, quiet general potentials, and they prove that under some potential theoretical assumptions, then this theorem holds. So we apply their theorem for our specific potentials.
Okay.
Is it clear?
Yes, thank you.
Okay. So so of course, in general, we can think of this problem for general potentials, but to obtain our theorem, we have to solve this inverse problem for the specific choice of the potential Q particular. Okay, and let me briefly review some of the background materials in potential theory to understand the idea of the proof. And one of the most important thing is the variation principles. So this is sort of the Euler-Lagrange type equations. So for when this zeta is contained in the drumlet, so in this at this point we don't know what is the drumlet here, but anyway, the Euler-Lagrange equation states that when for zeta inside the drumlet, when we consider this energy plus the external potential over 2, then it is always given by a certain constant. And also for general case, when zeta is outside of the drumlet, then this function is always bigger or equal than this constant. And actually, so this is the variation conditions. This is the variation principles, and this is very well known that the equilibrium measure can be characterized by this principle. And one another thing is the Laplacian growth. And actually, for general values of general class of the potentials, we know that the solution of the equilibrium measure problem, this probability measure is actually absolutely continuous with respect to the Riemann measure. And the point here is the density is always given by the Laplacian of the potential. And actually, this is you can observe this, for instance, from this here. So since the Laplacian of the logarithm is given by Dirac delta, so if it has certain density, then you can see that by taking functional derivatives here, then we can observe that at least inside the drumlet, the density should be always the Laplacian of the external potentials. So from this point, so this is the reason. So actually, so there is a reason that here the density part is almost trivial. So as I already mentioned in the statement of the theorem, so actually this density part is trivial because this is just given by the Laplacian of the potentials. So in this problem, the actual question is how we can obtain the support of this probability measure. And for the proof, let me recall what is the Schwarz functions in a given domain. So the Schwarz function is a unique monotony functions, of course, if it exists. And so the main point of the Schwarz function is it is same as the conjugate of the zeta on the boundary. And now let me explain the proof, the idea of the proof. And I think some of the audience are very familiar to these kind of equivalent problems. And for some of you are not, let me remark that actually, okay, so for instance, when the potential is radially symmetric, then this problem is very simple. So because for the radially symmetric potentials, then the drumlet is basically given by either disk or possibly annulus. So all of this solution is well known, but actually for non-radially symmetric potentials, there are very few explicitly known examples of these solutions. And somehow all of these examples comes from the theory of the Herleshov flow. And so you can think of some special class of the potentials, which is given by Gaussian plus some harmonic terms. And but anyway, we obtain our result by we actually borrow some ideas from this theory. And to do this, we actually have to assume that the complement of the drumlet is a simple conic domain, because we have used so-called the conformal mapping method, which I will explain now. So under these assumptions, so again, at this point, we don't know what is this this drumlet, but under these assumptions, we can take a Riemann map, which maps the outside of the disk to the outside of the drumlet. So we would like to know what is the explicit formula for this conformal map, and of course to indicate.
Okay. I think there is a problem with the microphone, or I don't know if it's a problem with your microphone or with my my line, but there was some.
Okay, so can you hear me? Or
yes, but probably it started to fry at some point.
So is there a?
I don't know if it's
back here.
I think now it's fine.
Okay. Okay, so then let me continue. Okay, so we take this kind of Riemann map, and we require this kind of normalization near the infinity. And so this positive constant is called the conformal radius of the drumlet. And so let me explain the basic strategy, general strategy to obtain what is this conformal map. So the first idea is we would like to define the analytic continuation of this conformal map to the whole plane. And then let's say we know all the information of the poles of this Marchenko function in the whole plane. So for instance, we know how many the poles and where, and also for instance the orders and all the residues, for instance. Then basically by rules, we know what is this Marchenko function exactly. So this is the general strategy, and as a first step, so we have to define the analytic continuation, and this is the point we need the concept of the Schwarz functions. And first, to define the analytic continuation of this kind of conformal map, we require what is the Schwarz functions. And of course, at this point, we don't know explicit formula of this Schwarz function, but using the variational equality or the Euler Lagrange equations, we can obtain that the Schwarz functions can be expressed in terms of the Cauchy transform of the equilibrium measure. So you can. So of course, we don't know what is the equilibrium measure at this point, but anyway, we can see that the Schwarz functions can be expressed in terms of this Cauchy transform in this way. And using this type of interrelations, we can define the analytic continuation of the conformal map to the whole plane, and also actually thanks to these expressions, we can also determine that this Merope function has only poles only at 0 and infinity, and also we can also determine that all of these poles are actually simple. And the final remaining step is to obtain the residues of each pulse, and also we need to calculate the constant term here. And to obtain this, we compute some asymptotic behaviors of this Merope function near the origin and infinity, using the variation equality, and also using the trivial fact that this the equilibrium measure has total mass 1. Then we can actually obtain the residues at each pulse, and also the constant terms. So so in this way we can obtain certain interrelations between these coefficients, and we can solve these algebraic equations to obtain the explicit constants. And actually, if we have these terms, then we can see that this is the shifted or translated Joukowski transform. So this is when we see this as a conformal map, then this maps the unit circle to the boundary of the support, in this case the ellipse. So this is the way we can find the candidate of the drumlet. But in the proof of this theorem, I already mentioned that when we use this kind of conformal mapping method, so this method relies on the basic Riemann mapping theorem. So we have to always assume the connectivity of the drumlet. But and then we can obtain this kind of a unique candidate, and then we actually show as a final step, we actually show that this is simply connected by using again the variational conditions. And actually this is because for general class of the potentials, as far as I know, there is no fully general theory on the connectivity of the drumlet. And as far as I know, the only general theory on this kind of connectivity of the drumlet is for the Hellatio type potentials, which was given by Singyab-Lee and Makarov. But anyway, in our case, our potential is not of Hellatio type, so we cannot use this theory developed in this paper. So we have to actually show that they are simply connected domain. And indeed, this is actually the most technical part in this proof. But I think anyway, in this way, we obtain the theorem I present in the first part. So this is the first part of my talk, and let me move on to the second part. And is there any other questions about the first part?
Sorry.
Can I ask a question?
Sure.
So it's typical that in those problems in random matrix theory, when you have to compute like some, because like you have like the Coulomb gas picture, you compute the equilibrium measure, and people also look at the mother body or skeleton, which typically also has some interpretation in terms of the matrix model. Have you looked at that for your equilibrium measure?
So once again, you mean at the skeleton?
Yes, exactly.
Yeah. So okay. So I understand your point. For instance, in a work by in the work by Kyler, Delay, and Quillers, they also consider skeleton, if I remember correctly. But so far we haven't considered these in these models. But actually, okay. I see.
Yeah, there are actually several words that consider that, but if you haven't, no problem.
Yeah, sure. But okay, we haven't. So
Yeah. Yeah.
okay, thanks for the questions.
Yeah.
And is there any other? Okay,
No,
then.
I had a question just of probably philosophical, but so now you would try to. I mean, probably you will not explain that, but one would try to prove the simple connectivity just by so what would be the assumption that that the domain S alpha does. So what are the assumptions on S alpha? So to start proving the simple connectivity.
Okay, right. So in the proof, we first take some conformal map outside of the disk to the outside of this S alpha. So for this, we did these connectivity assumptions.
Yeah, of course.
Okay, is it clear?
Yeah, this is clear. But so without so now you would prove the simple connectivity. But so for the simple connectivity, what would be the assumption? So
actually, I think I don't understand your question.
So you cannot you would assume that the variational principle is correct. You would assume that the Laplacian growth is holds. So what do you remove once you do not have?
Okay, so Laplacian growth is always correct in this case, and also actually the first because of this characterization theorem of the equilibrium measure, these all-around equations, then if we have some candidate of the solutions, then we can actually directly check if this is the correct answer or not. So to obtain this candidate, we first assume this connectivity, then we obtain this candidate by using this conformal map, and then we again have to check these variational conditions. So this is the story of the proof.
Okay.
So so in this way, there is in the theorem there is no assumptions.
So I decided, so instead of proving the simple connectivity, you just check that that the solution that you get by assuming simple connectivity solves the problem.
Right.
And then okay.
Okay, then let me move on to the second part. I think my talk will be a bit longer than I expected, but anyway, I will explain a bit more about the local statistics. And so in this case, we focus on the this critical regime. And just let me remind you that this multi-criticality, this what people multi-criticality appears in this critical regime, which has this kind of lemniscate type drumlet. And if we want to see the local statistics of the models, in particular, we want to see what is the local statistics near the origin. So in this case, we scale the point process like this. So in this case, we have to choose the nth power 1/4 is the correct scale, and so this blue dot denotes the original point process, and we define the rescaled point process by simply dilating. And of course, as in the random matrix theory, we want to understand what is the k-point correlation functions, which is the normalized probabilities. We can find the particles at given positions in the Lagrangian limit. And about this, what we obtain is the large n behavior of the k-point correlation functions. We obtain the following. And for given any alpha, and when we have this critical regime, then we show that the limiting k-point correlation function is expressed in terms of the determinant of the correlation kernel. So basically, this is the determinant point process, and the point here is the k-point correlation function is given by these functions. So we have this polynomial square term here, and also squaring of the Gaussian terms, and also complementary error function terms here. And actually, there are several related works in this regard. And in the case of the Hermitian matrices, in particular the multi-critical unitary ensembles, then the local statistics of this kind was first obtained by Blair and Itz, and the universality problems in this region was obtained by Clay, Squillers, and Bellassen in paper 2006. And actually, recently there are several works about the planar ensembles containing this kind of singular boundary point. And for instance, in this work, well, this is the work published last year. They consider the local statistics near the cusp type singular boundary point, and also in a work by Barlow, Bertula, Lee, and Magnorin, they consider they also consider they also solve certain equilibrium measure problem having cusp type singularity, and also they obtain the strong asymptotic of the orthogonal polynomials. And also in a work, some work by Barlow and Merzi, they construct some sort of general way to construct singular boundary point. And also in a very recent work of Diano and Sim, they consider characteristic polynomials of this kind. And anyway, this is the theorem we obtained. And let me briefly show you the transition of the local statistics in these three different regimes. And again, we can think of the local statistics at the origin and rescale the point process. And what we can obtain is the following. And so the previous theorem states this critical regime, and we have this non-radially symmetric type of the one-point functions. So basically, because of this feature, there are more eigenvalues near this line. And actually, in the pre-critical regime, the density is given by radially symmetric functions, actually given by the square. And of course, at the post-critical regime, we have the vicinity near the origin. So in this case, the rescued point process vanishes. And the counterpart, again, the equivalent formulations for the non-Hermitian Vicharta ensembles is as follows. So just for the recur, what we call the critical regime in this case corresponds to the case that the origin is on the edge of the spectrum. So we again consider the rescued point process. And in this case, because the density is of order O1 at this point, so in this case we have to choose the scaling order 1/1/2. And again, we can think of the correlation function, and we denote by R hat. And then we can actually show that in these formulations of the non-Hermitian Vicharta ensembles, we have this kind of uniform convergence, and where actually in this case the correlation kernel is given by the well-known Ginibre kernels. So as many of you probably are familiar, so this kernel appears in the edge of the spectrum of the Ginibre point process, which was first obtained by Forrester Honor, as far as I know. And some other related works is in the case of the determinant of Coulomb gases, so which I mean the Coulomb gas with inverse temperature beta = 2, then the local universality problems it was obtained by Heidelman-Makarov for the bulk universality, and for the edge universality, this was obtained by Heidelman and Bellman. And now let me explain how we can obtain these theorems. And actually, the determinant, so the determinant structure is obtained by definitions. And for the recur, what we call the determinant point process is if the correlation k-point correlation function can be expressed in terms of the determinant of some correlation kernel. And then and again, so if we define this kind of rescaled point process, then again, this rescaled point process is also the determinant process, and these two this can be related to the original kernel in this way. And here we can use the techniques using the orthogonal polynomials because of the Dyson's determinant formula, which I believe all of you know. So we can express this kernel in terms of the orthogonal polynomials. Of course, in this case, these orthogonal polynomials with respect to the weighted measure in the plane. And then, so now the problem is, what is the orthogonal polynomials for our model, the Richard and matrices? And actually, this is the point here. So for the Hermitian matrix, you know that the Richard ensembles can be solved using the generalized Laguerre. And actually, one of the reasons the model we are working on is the natural extension of the classical Richard is actually the associated orthogonal polynomials for this weight. And so you, for the record, this is the weight function. This is the Bessel K functions. And actually, if we consider the generalized Laguerre polynomial with complex variables, then it satisfies these orthogonality relations with respect to this weighted measure. And actually, this is highly non-trivial, and this was obtained, partially obtained by Gernot in 2002, and also obtained by Osborne in 2004. And and one small remark is, in the Hermitian matrix models, when we consider the orthogonal polynomials on the real line, and there are a bunch of orthogonal polynomials, well-known or classical orthogonal polynomials with also well-known weight. But when we consider the orthogonal polynomials in the complex plane, and in this case, as far as I know, there are only 3 explicitly known weight functions. And of course, the first example is the arithmetic polynomials obtained in a paper by these two in '98. And actually, this is the first point for federal precision consumers to study the elliptic Ginibre ensembles, which is the non-Hermitian extension of the Gaussian unitary ensembles. And the second example is this generalized Laguerre with this weight, and also one another example was obtained quite recently last year in work by these guys, and then they obtained the Ginibre polynomials, which is the symmetric Jacobi polynomials, having some special weight. And actually, using these, they also consider the generalized truncated unitary ensembles. And anyway, the point here is using these nice orthogonality relations, we can study the correlation kernel using this Laguerre. And one more, actually, there are some several functional relations we need about the Laguerre polynomials, but one of the most important part, the functional relations is as follows. So we can, so when we consider this product of these two Laguerre, then this can be expressed in terms of the summation, weighted summation of the single Laguerre polynomials having this type of arguments. So this is sort of classical but not that well-known function relations. And actually, at this point, you can observe that this G plus W bar argument will help us a lot, because basically using this Dyson's determinant formula, we have to compute this kind of guys, the summation of these generalized Laguerre. And then in the end, we want to obtain the this boundary Ginibre kernel. So it is sort of natural to see this kind of argument. And anyway, this is the one function relations we use. And the other is very well known. We also use very well-known counter-integral representation of the generalized Laguerre polynomials. And then combining all of these formulas here, we can express the correlation kernel we want to analyze in terms of these summations. And here, these terms comes from the potentials, and using the generalized, the counter-integral representations, we obtain that the summation is given by this some summation some certain functions, which is given by this counter-integral. And basically, the main techniques we use is just the steepest descent method. So so we use the well-known steepest descent. So we find the we deform the contour in a nice way to pass through the saddle point of the dominant part of the these functionals. Then in this way we can show that it is asymptotically given by this. So as you know, when we use this steepest descent, then we can analyze the dominant part of this kind of contour integral in terms of the real integral representations. And then this is one of the integral representation of the error functions. So in this way, we obtain these complementary error function terms here, so which gives square G plus W bar over square 2. And we actually did some more analysis here. And first, we showed uniform boundiness of these functions when we restrict this on the negative real line. And then using this uniform boundiness, we can show that this correlation kernel is asymptotically same as these terms. And then, and also the final step here is we also calculate some asymptotic behaviors of the modified Bessel functions of first and second. And then in this way, we obtain the theorem I showed before. So basically, these terms contributes to the these Gaussian terms here. So in this way, we obtain the local statistics at this criticality. And let me end this talk by mentioning some of the works in progress and outlooks about this work. And okay, one of our current work is we want to describe. So during the proof, we when we consider the global statistics, we only use the Coulomb class interpretations. So actually, the first part, the global part, also hold even for general beta, even for general Coulomb classes. And so we also try to obtain sort of analogous problems for the local statistics in a different symmetry class. For instance, we are or quaternion, and especially we are focusing on the quaternion case. And as a preliminary work of the quaternion version of these matrices, we obtain the local statistics of the quaternion Ginibre ensembles at the right or left end point of the spectrum. And actually, we also obtain some other things about when it contains some singular point, some conical type singular point. And also with Gernot, Marcus, and Ivan, we also work on the universality problems for the quaternion elliptic Ginibre ensembles. And some more problems one may consider is of course, the universality problems for beginner type matrices. And here in my talk today, we only focus on the Gaussian matrix models, but of course we can think of the beginner type matrices. And as you know, if we consider these beginner type matrices, we cannot use these Coulomb-Gauss representations, but of course we can expect certain universalities phenomenon happens. And also there is another direction one may consider is the dynamical extensions. So actually, quite recently, this year, May, there is some work in Japanese group about the dynamical extension of the elliptic Ginibre matrices, and actually they asked me how we if it makes sense to consider this kind of dynamic extension also for the model we are working on. So especially if we have this kind of limiting global spectral distribution, then we can also think of analogous type of planar Dyson type Brownian motions. So this is one of the topics one may consider, and I think this is what I want to talk about today. And thanks a lot for your attention.
Well, thank you very much. Appreciate the talk a lot. Somebody's clapping. So let's see if there are some additional questions.
Yeah, I have a question, Sung-Soo, if I may.
Sure.
You have considered the case for the free boundary ensembles, right? And then you have using the formalism to find the shape of the droplet. Have you done some work in the case of hard H ensemble?
Okay, all right. Actually, it's a very good question. So so for some other audience, what we call the hard H ensembles is we redefine the potentials. So in some part of the complex plane, we redefine the potential as infinity. So we do not allow the particles. So we completely combine all the particles in given domain. So this is the one of the construction of the hard H. And for your question, when we consider the hard H, so by definition, if the hard H is if we make this kind of hardware which is bigger than the drumlet, then actually the equivalent problem is same as before. So the solution of the equivalent measure problem is always same. But in other case, when we consider the hardware inside, and also there is another theory in potential theory. So when the hard H is completely inside the drumlet, then we can the solution of the equivalent measure, the solution of this inverse problem is given by combination of the 2D planar measure, and also there is certain measure supported on the boundary. So and actually this measure can be described by Bailliage measure. But the most hardest part is when this hard H is somehow between these two regimes. So when we consider, for instance, okay, let's say if we say all the particles should have to be right half plane, then of course, we can think of this kind of equivalent problems, but to solve this question is, I believe, widely open.
Sorry, say again. Sorry, say again.
So okay, so you understand this theory regime, right?
Mm-hmm.
And the most difficult regime is definitely open for even for a very simple the most simplest case, even for the Ginibre matrices for the circular law. If we consider this kind of hardware, this is open.
Okay.
So you have considered this. You have computed this limiting kernel in the case of the kernel K that you presented with the error function. So this is the limit of the determinant point process at the around the origin. So are there other interesting location to look for interesting kernels?
Oh,
For
okay,
example,
right. Okay. Actually, it's also very good question. But when we consider another point, then so when we consider this Dirac picture, only at the origin this kind of scaling kernel appears, some new kernel appears, and all of the other point we have we have the classical Ginibre kernel. Because okay, there is no proof, but we can easily expect, because actually for the Dirac matrix, the eigenvalues interact via the has sort of some scalar interaction, and actually this local interaction influence affect only at the origin. So the point here is the origin is really special point for this model, and beyond the origin, we expect the classical universality class appears.
okay.
Hi, Sung-Soo. I have one question.
Yeah, please.
So, because you talk about the droplets and the equivalent measure, and also you mentioned some orthogonal polynomials. Do you think there will be some Riemann-Hilbert problem related?
Right. But you know, you are more expert on the Riemann-Hilbert problem than me. So okay, I believe. But okay. Actually, so actually in this case, I understood the reason we in our proof for the local statistics we don't have to consider the Riemann-Hilbert problem is actually in this case we know exactly what is the orthogonal polynomials, so we don't have to try to obtain the strong asymptotic for the orthogonal polynomials. As I mentioned before, we have this the classical Laguerre polynomials is really the right answer. So that's the reason we can solve this problem in this way. But yes, in some other, when we consider some other stuff, yes, definitely there will be some Riemann-Hilbert problems. But yeah, let's discuss a bit more later.
Okay, all right. Yeah, because I can see the external potential, the formula is a little bit complicated, so I'm not sure whether it is related to the Hilbert, but the analysis, whether you can that can be done. I'm not sure for that. And also, do you have any result related to the partition function part?
Oh, right. Actually, so in case of the partition functions, it is we actually have explicit formula for the partition function in this case. because you know, so when we have the when we can calculate the norm of the orthogonal polynomials, then basically the partition function can be obtained by product. So you know the so the partition function can be obtained in can be expressed in terms of the product of the orthogonal norms of the monic polynomials.
Right.
And in this case, we know what is the this norm.
Mm-hmm.
So basically, this norm is combination of the gamma functions. So this this norm can be expressed in terms of the gamma functions. So product of the some gamma functions. So I think so of course the partition function can be expressed in terms of the Banner's G functions. And yes, so in this case, the partition function can be easily computed in a very special, very precise way. And if you think, so maybe you are asking the Lagrangian asymptotic of the partition function, right?
Yes, because when you mentioned about the Coulomb gas, about the expression, and there is the normalization constant. I think in your slides you mentioned Zn hat.
Right.
That's the term I'm asking.
Yeah, right. So when we consider these the partition functions, then we can also think of the Lagrangian expansion of the free energy, and of course the definition of the first term and square term, the coefficient is given by the weighted energy of this equilibrium measure, and you know the second term is basically given by the entropy, but I think there in this case there is some more terms beyond the entropy. Because if you remember the formulas of the potentials, the potential itself depends on the number of particles n. So these also may affect the subleading entropy terms. And
okay.
yes, yeah.
Okay, thank you.
Okay, so probably if there are no further questions, maybe we can thank Sung-Soo again, and yeah, and okay, so it seems that there are no further questions. So yeah, thank you very much for joining, and yeah, hope to see you soon, and see you around.
Thanks a lot for attending the talk.
Bye bye.